Okay, we're going to start with the datum. So last time we left out with the datum, so we will use this for the datum. Spheroid, we will talk about spheroid, datum, projection, and coordinate system. So how to locate the geographic location. So it's very important to understand that our Earth is spheroid. It's a 3D. So how the 3D model is related to the shape of the Earth, that we will use the datum. So a model to translate the 3D points on a 2D surface with minimal distortion is projection. We will talk about projection, and a coordinate system to measure the points 3D or 2D. Alright, so I really enjoy this SOB, and because let me show you what is SOB. It's right here. So SOB is right here, and the only thing is that the debut, they're gonna charge me money, and I did some search on YouTube, and thanks to the YouTube people, and so I'm gonna go to my history. So go to history, and the OBS Studio and the top free screen recorders, those are the best. This one talked to you a lot, but I really enjoy his video, and he showed me how to use it, and now I'm on my way. So thank you so much. And now I'm gonna do is I do have a debut, I think debut recorder. So I downloaded. It's easy to use, but after a while they charge you money. So the best free screen recorder, it's not totally free, because it was just maybe the first or 2 days or the first 2 hours. But I do enjoy that one. But yeah, like the video says, as OBS is free, open source, but debut is kind of crazy. It's not free. Okay, we will back on our datum. Datums, I don't know if I pronounce correctly. So the datums, a geographic coordinate system is defined by 3 things. So an angular unit measure, usually degrees, and a prime meridian, usually Greenwich, and a datum. So the datum is the part that gives people trouble. So to understand it, we will start with the shape of the Earth. So the Earth isn't a perfect. The Earth is not a perfect sphere. So here it should change. Earth is not a perfect sphere. So Earth mass is not distributed uniformly, so the gravitational pull is not uniform. And due to rotation, equator is slightly bulged, and poles are slightly flattened. So oblique, spheroid, and terrain is not uniform as well. So the Earth is not a perfect sphere, so even a mathematically regular spheroid, it's a lump with an uneven shape owing to different concentration of mass, and therefore unequal gravity over its surface. In addition, it has topographic features such as mountains and valleys. So can you tell me, in this case, if you are near the equator, you will be heavier, and that's why, I don't know whether it's true, that's why near the equator you have heavy gravity. So near the equator, people are shorter, and away from the equator, people are tends to be taller. So I don't know whether it's true, but maybe in Asia, some people feel it is true. Okay. So highest spot on Earth. And the tallest peak on Earth, the Mount Everest, is AA48. But now they bump into AA450 meters above the MSL. So, and then what is the highest spot on Earth? Where are you the closest to the outer space? So they say it's Mount Chimborazo in the Andes, 6,100 meters above mean sea level. So, but it is sitting on a bulge, which makes it 20 1,400 meters taller than Mount Everest. Everest is sitting down on the lower side of the same bulge. Alright, so look like this. It's very interesting. So, that we have when the spatial positions of features are determined, as was formerly done by survey and it is now mostly done by satellite, they are first determined on the Earth's surface. These raw measurement values are then mathematically leveled to a joule rate. A joule rate is the still gravitationally lumpy shape that the Earth would have if it was covered by a mean sea level surface. So MSL is mean sea level. In other words, it had no topography. So the shape of the joule rate, however, is too complex to be working model. So the next step is to move the measurement from the joule rate to a spheroid, a model with a regular non-lumpy shape. So joule rate, we have the Earth, joule rate, and spheroid. So now, this slide is cool. Look at the picture. So shape of the Earth, we think of the Earth as a perfect sphere when it actually ellipsoid, spheroid, slightly larger in radius at the equator than the pole. So Earth model, we have a flat Earth and survey over a short distance, spheroid Earth approximate global distance, and spheroid Earth accurate global distance, and joule rate surface of equal gravitational potential. And the Earth's surface, so let's look. Joule rate is a surface of constant, is that joule rate minus topography, so kind of like we smooth it out. It's a surface of constant gravity. Okay, so and taking into account all these irregular is different. So taking into account all these irregularities is different. Some irregularities can be ignored. For example, terrain through important locally terrain levels are minuscule in planetary scale. The tallest landmark stands less than 9 kilometers above sea level, or nearly 1/1440 of Earth's diameter. The depth of the most profound sea abyss is through 1/1150 diameter, 1,150 diameter. So the ellipse you calculated was defined that focal length is, I forgot how to pronounce this, phi, and flatten ratio is F equals alpha minus B divided by A. So distance, we will have the F1 minus P minus F2 is constant for all points P on ellipse. When the theta is this side, equals 0, then ellipse circle for the Earth, major axis A and 6,378 kilometers, minor axis is B, 6,357 kilometers, flatten ratio, the kind of like you calculate as F equals 1/300. So let's see the Greek symbol and pronunciation. So Greek symbol. Okay, I'm sorry, I forgot. Epsilon. Oh, epsilon. Yeah, epsilon. Epsilon. Alpha, beta, gamma, delta. Oh, this is delta, and epsilon, theta, zeta, eta, theta, iota, kappa, lambda, mu, nu, c, opsicron, pi. Yep. Oh my god. Omega. This one. Psi. Okay, this psi. Chi. Chi. Oh, this is chi. Chi. Phi. Phi. Upsilon. 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 Tau. 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 Okay. Oh my god, those are crazy. Okay, let's back here. Oh, I forgot again. I'm sorry. I'm not a good person. Epsilon. Epsilon. Yeah, epsilon. So epsilon. So that selected reference ellipsoid that Mount Everest and ellipse that they changed it until the WGS. So flattened, and they use 1930. They use the Mount Everest. Okay, so why use different spheroids? So the Earth's surface is not perfectly symmetrical. So the semi-major and semi-minor axes that fit one geographic region do not necessarily fit another. Satellite technology has revealed several elliptical deviations. For one thing, the most southerly point on the minor axis, the South Pole, is closer to the major axis, the equator, than the most northerly point on the minor axis, the North Pole. So let's look at here. So the Earth's spheroids deviate slightly for different regions of the Earth. Ignoring deviations and using the same spheroid for all locations on the Earth could lead to errors of several meters, or in extreme cases hundreds of meters, in measurements on a regional scale. So Mount Everest, that India, Nepal, Pakistan, Bangladesh, and so for the WGS, GPS Worldwide and Clock 1866 North America, and GRS 80 North American International 1924 Europe, and the Europe also have the, I think it was Russell. And Mount Everest 1930, the Colonel Sir George Everest is the name of the Surveyor General of India. The Great Trigonometric Survey India, and sometimes referred as Indian datum, has been modified several times since. And WGS 1984, used by GPS, need for a common global system. And Great Trigonometrical Survey, the idea 1945, General Roston 1802, real commencement and baseline is 4,006.4 feet on the plain near St. Thomas Mount, Madrid. From this, a series of triangles were formed, 30 to 40 miles in length. The objective is to find the curvature of the Earth accurately at different latitude and longitude. Everest 1830 spheroid. So look at this and the datum. So now finally we get to the datum. And previously we just talked about, let's go back a little bit. So previously we talked about the datum that comes in. So why? The data comes in, the datum is two things. First, it is a chosen spheroid, which could be WGS 1984, GRS 1980, and Clark 1866, and Bessel 1841, or a number of others. So that we went through here, and the world is standing on the GRS 1980 spheroid, but it isn't all the way there yet. So second, a mathematical orientation or fit of the georoid to the spheroid. In the transfer of measurements from georoid to spheroid, some error will be introduced because the lumps must be smoothed out. Wow, so I know it's a lot to learn, but let's look closely. So reference frame for location points for Earth's surface. So the datum define origin and orientation of latitude longitude lines, and defined by spheroid and spheroid's position relative to Earth center and Earth centered local. So how that error is distributed is the fit one approach to make the fit really good for one part of the world, such as North American, and not to worry about the rest. This is a local data, and it's designed to maintain high accuracy for measurements over a limited area. The other approach is to average the area over the whole surface. That is an Earth-centered datum. So, good overall fit. It's designed to maintain high accuracy for the world as a whole. So now we're gonna look at for maps covering very large areas, especially worldwide. The Earth may be assumed perfectly spherical since any shape in precision is drafted by avoidable errors in data and media resolution. Conversely, for very small areas, terrain features dominate and measurements can be based on a flat Earth. And the datum, horizontal datum, or geodetic datum, reference frame for locating points on the Earth's surface, define origin, orientation, or latitude, longitude lines, defined by spheroids as spheroids' position relative to the Earth center. And two types of datum, Earth-centered and local. And look at this local coordinate system, Earth-centered datum coordinates. Earth surface, so Earth surface, like it's up and down, and the local datum, we have a NAT 27 in WGS 84. So, okay, the data, a mathematical model must be related to real-world features. So a datum is a reference point or surface against which precision measurements are made, and an associated model of the shape of the Earth for computing positions. A smooth mathematical surface that fits closely to the mean sea level surface throughout the area of interest. The surface to which the ground control measurements are referred provides a frame or reference for measuring locations on the surface of the Earth. And how do I get a datum? So to determine latitude and longitude surveyors level, their measurements down to a surface called a geoid. So the geoid is the shape that the Earth would have if all its topography were removed. So, or more accurately, the shape of the Earth would have if every point on the Earth's surface have the value of mean sea level. Indian datum, Kalilampur Hill in Madhya Pradesh, a spheroid at Mount Everest. So let's look at here. So this is Earth, location measured on Earth. We have everything, and geoid like Earth without topography, so you kind of smooth it out. Ellipsoid and a transfer to the ellipsoid, and everything is moving into a more perfect mode. And the horizontal versus vertical data. Horizontal datums are the reference values for a system of location measures, for example, longitude and latitude. The horizontal datum is the model used to measure positions on the Earth, and vertical datums are the reference value for a system of elevation measurements. So the vertical datum is used for measuring the elevations of points on the Earth's surface. And vertical data. So vertical data are either tidal level based on sea levels, datum, gravimetric based on the geoid, or geodetic based on the same ellipsoid models of the Earth used for computing horizontal data. So definition of elevation. So the mean sea level is right here, and geoid, and elevation is measured from this geoid. And now we're going to move to projection. So when two geographic coordinate systems are different, it's usually because the data are different, which in turn it's either because of the spheroid are different or the fit is different. When we get to a coordinate system warning, in ArcGIS Pro, one possibility is to ignore it and leave the data slightly out of alignment. Depending on the needs for accuracy, this may be an entirely sensible choice. The amount of misalignment depends on the data involved and the part of the world being mapped, but in the mismatch that world Americans usually encounter between the World Geodetic System of 1984 and the North American data of 1983, it typically doesn't exceed a few feet. So at most scales, the difference is not noticeable. The other option is to reconcile the system through a geographic transformation. Transformations are often done in conjunction with a coordinate system projection. Like projections, they can be permanently applied to data sets with data processing tools, or they can be done on the fly in ArcGIS Pro later. I think I already did define projection. So the transformation requires some expert knowledge. There are default methods to convert one spheroid to another, but there are not default fits because the right fits depends on the area of interest. So it's important to know that because the right fits depends on the area of interest. The table on graphic datum transformations that it's online, and we can find the area of interest. I think there was a PDF documentation if we search, so we will know its ID, which area you use, and you put your location in. And actually, you could just put your location. So let's see, for example, I would say state plane projection for Jacksonville, Florida. Okay, so now there it will tell you what kind of zones they use. So this is really nice. State plane, Department of Transportation, and this is cool. And I think it just ArcMap. They produced by Department of Transportation. I'm gonna download it here, and this is really cool. And the color, I really don't like it. Shouldn't use blue or something, or some other color. Tampa districts, I don't like the color. I would use other color instead because it's very close to the water color. But other than that, let's see. Map, title. Cool. I would put something later. Okay. State plane transfers Mercator, Lambert. I don't see any difference yet. Okay. Expert GPS, Florida, west. Okay. So for Florida, we do have east, feet in Mercator meters. Yeah, we have east, and we have north, and we have a west. So cool. Then if for Jacksonville, we are in the northeast. So coverage. So let's see, Duval is here. So then we use east. Florida east. So coordinates, latitude, longitude. Cool. Okay, so now let's back in here. So for the projection, we talk about that, and we will continue with the projection. So the geographic coordinate system, spherical Earth surface, radius, the Earth's radius is 6,371 kilometers, and meridians, lines of the longitude, and that's we call meridians, and passing through Greenwich, England as prime meridian or zero longitude, and parallel lines of latitude using equator as a zero, latitude degrees, minutes, seconds, and we can use decimal degrees. So it will be DMS will be degree minutes, okay, to measure it. Okay, so the latitude and longitude we talk about on a sphere that we can use longitude, latitude. So we have a phi and lambda. So phi and lambda. So length on the meridian we can calculate same as latitude, and the length of a parallel varies with latitude. So example, what is the length of a 1 degree increasement on a meridian and on a parallel at 3 degrees north and 90 degrees west? Radius of the Earth is 6,370 kilometers. So the solution is 1 degree angle has first to be converted to radius. So the pi radius is 180. So 1 degrees you have a pi divided by 180. So you get 0.015. So for the meridian, and then you calculate it's around 111 kilometers. And for the parallel, you get 96 degrees kilometers. Parallel coverages as pole are approached. So the curved Earth distance, so shortest distance is a long great circle. A great circle is the intersection of a sphere with a plane going through its center, and spherical coordinates converted to Cartesian coordinates. So, and vector dots used to calculate angle alpha from latitude and longitude. Great circle distance is r, where the r equals 6,370 square kilometers. So the Earth centered, this is perfect Earth, but this is geodetic. We have the longitude, latitude, and the height. Okay, so projection. So the real world features must be projected with minimum distortion from around Earth to a flat map, and given a grid system for coordinates. So a map projection transforms latitude and longitude locations to x, y coordinates. Okay. And what is a projection? A mathematical transform from 3D objects into a 2D with a minimum distortion. So this two-dimension surface will be the base for the map. Okay, the Cartesian coordinate system, planar coordinate system, are based on Cartesian coordinates. Cartesian coordinates that you will learn in algebra class. So the projection spheroid to Cartesian coordinates with minimum distortion. So why use a projection? So can only see half of the Earth's surface at a time. You cannot go the other way around. Unless the globe is very large, it will lack detail and accuracy, harder to represent features on a flat computer screen, and it doesn't fold, roll, or transport easily. So type of projections. So we will have a conic, Albert's equal area, Lambert, and conformal conic, good for east and west land areas. That's for conic. And the transverse Mercator, it will be good for south and north and south land areas. Azimuthal and Lambert, azimuthal equal area, good for global views. So cylindrical, it will be good for north and south land areas. Okay, so the conic projections, Albert and Lambert. So conic, that it's like we use a flashlight on the top and look down, and central meridian and will look like this. And then Mercator, that we could do transverse and oblique, and it's good for north and south. And for the east and west, it will be Albert equal area and Albert confirm conic. So this is conic good for east and west. And then the cylindrical will be good north and south direction. And for the Lambert azimuthal, it will be good for polar so equatorial and oblique. Okay, the map distortions. So we distorted for shape, area, distance, and direction. So let's look at the projection distortion. Converting a sphere to a flat surface results in distortion. So shape conformal, if a map preserves shape, then feature outlines like country boundaries look same on the map as they do on Earth. An area equal area, if a map preserves area, then the size of a feature on map is the same relative to its size on the Earth. So on an equal area map, each country would take up the same percentage of map space that actual country takes up on the Earth. And distance, equal distant. So equal distant map is the one that preserves true scale for all straight lines passing through a single specific point. If a line from A to B on a map is the same distance that is on the Earth, then the map line has true scale. No map has the true scale everywhere. So let's look. So direction, azimuthal projection is one that preserves direction from all straight lines passing through a single specified point. So direction is measured in degrees of angle from the north. This means that the direction from A to B is the angle between the meridian on which A lies and the great circle arc connecting A to B. If the azimuth value from A to B is the same on a map as on the Earth, then the map preserves direction from A to B. No map has true direction everywhere. Okay, so the trade-off on an equal distance map, distances are true only along particular lines, such as those radiating from a single point, selecting as the center of the projection. And shapes are the more or less distorted on every equal area map. And sizes of areas are distorted on conformal maps, even though shapes of small areas are shown correctly. So polyconic, so like different columns. So the projection is based on an infinite number of cones tangent to an infinite number of parallels. The central meridian is straight, other meridian are complex curves, the parallels are non-concentric circles, and the scale is true along each parallel and along central meridian. And how projection is done. So the geometric projection is like this, and we put things and you can calculate things. And distant property preserved. Azimuthal equidistant projection, north polar aspect, Arctic at the center, and south polar aspect, Antarctic at the center. Only the radial distance from the center of the map to any object is preserved. So azimuthal equidistance projection, north polar aspect. So that azimuthal equidistance projection, south polar aspect. Azimuthal equal area projection, so that the area is better preserved. So azimuthal equal area projection, north polar aspect. So that you can see how it transformed. So on project latitude and longitude. So central meridian and selected by map maker and great distortion at high latitude. Example 2 thumbs lines, 2 rhumb lines, direction true between any 2 points equal. Equator touches cylindrical if the cylinder is tangent. Reasonably true shapes and distance within 15 degrees of equator. Okay, so now there are some famous projections like Mercator projection. So Mercator, it's good for north and south, not good for east and west. And Gall-Peters projection is famous, and Malawi projection, Miller cylindrical projection, and the Goody's Holmes law equal area projection. The Lambert azimuthal equal area. So the plane projection, we have the equator here, and we project like this, and so we can do polar. Mapmaker selects north or south pole, so we can see just north and south pole. An oblique mapmaker selects any point of tangency except along the equator or pole. Equatorial mapmaker selects central meridian. And Albert's equal area conic, two standards parallel selected by mapmaker. So, and this Lambert conformal conic, so standard parallel selected by mapmaker. The large scale maps that sheet can be joined at the edges if they have the same standard parallel and scales. Equal distance conic. So conic 2 standard parallel selected by mapmaker, distance along meridian and standard. So universal transverse Mercator uses transverse Mercator projection. So a 60-degree wide zones covers the Earth from east to west, starting at 180 degrees west, extending from 80 degrees south latitude to 84 degrees north latitude. So each zone has a central meridian. So units are meters. So they use meters for the UTM, Universal Transverse Mercator. The 60-degree zones, I think it was developed by the Army Corps engineers. So transverse secant cylindrical Mercator projection, and the UTM zone numbers. So Universal Transverse Mercator, developed by the Army Corps engineers, and this is the one they use in UTM zone 14, central meridian here. Okay. And India, they used the Mount Everest and WGS 1984 projection, UTM and polyconic. So one projection to another. So the Earth, select reference. So that's how scale reduction, and that's how maps is being produced. Central meridian and forward mapping, inverse mapping. That's really cool. Inverse mapping, North Pole, and forward mapping. Okay, so I think the projection is more. This is very good. And let's see. Okay, we did the data, and next we will talk about geodatabase for around 1 hour, and then I think we will go from there.